In this lesson, we're going to talk about the vertical mass on a spring and the simple pendulum. Up until this point, we've looked at simple harmonic motion by investigating masses on springs that are oscillating horizontally on frictionless surfaces. So now let's ask if a vertical mass on a spring is also oscillating with simple harmonic motion. So here's an example of what we're talking about. We've got a mass on a spring oscillating vertically. We're going to assume, as we did before, that the spring itself is frictionless. And really the question is, how does gravity affect this situation? And does that change this from being simple harmonic motion like it was when it was a horizontal oscillation? Here we have a spring attached to the ceiling and there's no mass on it, so this is its natural resting length. But then we hang a mass off of it and that's going to extend or stretch the spring, but here it's not oscillating yet. We've just gently placed the mass on, and that's going to displace it from equilibrium by an amount x. I'm going to call the initial displacement from equilibrium x. Now for this to be at rest, for it to be not oscillating, not accelerating, we need to have a net force of 0. The upwards force is provided by the spring, and the downwards force, of course, is gravity. I'm going to call this F spring 1 because it's our first situation, in contrast with the second situation that we'll look at in a moment. So the spring force in our first case is equal to k, the spring constant, times x, the displacement from equilibrium. That's by definition, or from Hooke's law. And because the net force must be equal to 0 for no acceleration, there's no acceleration in this case, we must have our upwards force, which is equal to kx, that's our spring force, equal to our downwards force mg. mg being the weight of the mass on the spring. So kx minus mg is equal to 0, or kx is equal to mg. Our upwards force, the spring force, is equal to the downwards force, the weight of the mass. Now let's perturb the system. I'm going to take my hand and I'm going to pull it down further from this resting length. So here it was just at rest, now I'm pulling it down further, and although my hand's not shown here, I've pulled it out of equilibrium to a new position. So this is the initial displacement from equilibrium left over from before, but now I've pulled it by this new amount, delta x. And in this case, if I were to let go, it would spring up and start oscillating backwards and forwards. So there is going to be an acceleration. And this is not going to have a free body diagram with forces that all cancel out. So what are the forces on the free body diagram? Well, there's a new greater spring force pulling it upwards, greater because it is extended by a greater length than it was in case 1. And there's still the weight of the mass pulling downwards. So what's the new spring force equal to? Well, it's going to be equal to the same spring constant as before, multiplied by the total displacement from equilibrium. Remember, the initial equilibrium position was up here. So now it's been displaced by x plus this new delta x. And multiplying through, I get kx plus k delta x. So that's the new spring force in this second case. The net force is the spring force minus the weight. So the spring force is equal to kx plus k delta x. This is the spring force here, and that's pointing upwards. And then I've got the weight pointing downwards. But the kx part of the spring force we said was equal to mg. So pulling this over from our previous equation and substituting in, this kx crosses out, it becomes mg. Now we have two mg's, mg plus k delta x minus mg, and these cancel out, and I'm left with k delta x. Delta x being the displacement from the new hanging equilibrium with the mass attached. So you can see there's an upwards force in this case that is equal to k times the displacement from this equilibrium position. Looking at this, it's as if we were to completely ignore the first situation and just start from this as our equilibrium position, we now have our displacement from equilibrium position here showing up in our F-net equation, just as we had before with the horizontal mass. So this has exactly the same form as the horizontal mass oscillating. In other words, it looks once again like Hooke's law, and we're going to get simple harmonic motion as a result. So the vertical mass on a spring exhibits simple harmonic motion, just like a horizontal mass does. Now let's look at a simple pendulum. Here's an example of a simple pendulum. We see a mass at the end of a string oscillating backwards and forwards. This is another simulation from PhET. To understand the next part, let's just quickly review the definition of the angle theta in radians. If we're working in radians, the angle theta is defined as the arc length divided by the radius of the circle that you're working in. So if this is a circle and we sweep out an angle theta here, then that angle theta is equal to this arc length, which I'll call s, divided by the radius of the circle. That's going to come in handy in a moment. Here's a diagram of a simple pendulum. Here's the pendulum here and the string, and I've illustrated some of the forces and broken them down into components. The angle theta we're going to call the angle between the vertical and the string. And the equilibrium position is over here, and I've moved it to one side, and I'm going to let it go and let it start swinging. If we orient our axes along the tangent here and radial in the circle, in other words, along the string, then this angle theta appears over here as well. And the two forces acting on this pendulum are going to be the force of tension operating upwards along this string. That's the force of tension. And there's also going to be the force of gravity, or the weight, operating downwards. And I'm going to break the force of gravity, the weight, into two components. The horizontal component here, and the vertical component here. Horizontal and vertical relative to my orientation of the axes. So this has gone away because I've broken it down into the two components. Now, we need to ask ourselves, what's the restoring force here? Well, the restoring force is the tangential component, this component here, of the weight. And using trigonometry, we can see that that's equal to mg, the weight, sine of theta. We're swinging this weight up in this direction, so to swing it away, we use sine. Or you can work it out from the right triangles. So the restoring force in this case is the tangential force, or the tangential component of the weight. So we need to ask ourselves, does that conform to the rules for simple harmonic motion? Well, what is that force? We've said that the tangential force is going to be equal to mg sine theta in its magnitude, and because it is pointing in the opposite direction from the displacement theta, it's got a negative. It is trying to pull us back towards the equilibrium position. That's where the negative comes from. Now, at very small angles, when we're working in radians, sine theta is approximately equal to theta. Here we're looking at two graphs on Desmos. The blue graph is just the line y is equal to theta. It's like y is equal to x, except my x variable is theta. And so we see that it's a straight line. The red graph is y is equal to sine of theta. And at small angles, in other words, in here, when we've got small angles theta, the two graphs are basically identical. Once you get bigger angles, once we move along the theta axis here, they start to diverge from each other. But at small angles, they're basically the same. So we call this the small angle approximation, and we say that sine theta is approximately equal to theta for small angles. And we're talking angles like 15 degrees or less, in which case we'll have an error of less than 1%. Using sine theta and theta as equivalent. So that means we can now replace this sine theta with just theta, which is approximately equal to. So the tangential force, our restoring force trying to pull us back into equilibrium, is equal to negative mg times theta. Well, let's take a look back here at the drawing and figure out what that angle theta is equal to. Remember that we said theta by definition is equal to the arc, so this arc here, divided by the radius, which in this case is equal to the length of the string. I'm going to call the arc x, so theta is going to be equal to x over L. This is the arc length, and this is the length of the string, or the radius. So substituting in then, we get our restoring force is equal to negative mg times x over L. Now if this is a force equation, I can get rid of that mass and get an acceleration equation. So our tangential acceleration is equal to negative g over L times x. And this has the same form as our defining equation for simple harmonic motion, which we've seen as negative omega squared x, where g over L is our omega squared. So g over L is equal to omega squared. So we have simple harmonic motion, or we have something close to simple harmonic motion because of this step. So For small angles, a simple pendulum will obey simple harmonic motion. As you get to larger angles, it becomes less and less accurate. Now, let's take this a step further and derive an equation for the period. If we think about the mass on a spring, we know that the period of a mass on a spring is given by this equation. T is equal to 2 pi times the square root of the mass over K, the spring constant. So let's derive something similar here. We know that in this case now, we've said that omega squared is equal to G over L. We also know that omega is equal to 2 pi over the period by definition. That's the definition of angular frequency. So T, rearranging from here, T is equal to 2 pi over omega. Well, what's omega? Omega, from here, must be equal to the square root of G over L. So 2 pi over the square root of G over L. And flipping, because we're dividing by a fraction, we get the period of a pendulum is equal to 2 pi times the square root of the length of the pendulum divided by the acceleration due to gravity. And this result, which looks very similar to the result for a mass on a spring, but this one's for a pendulum, tells us that the period of a pendulum doesn't depend on its mass and doesn't depend on the amplitude with which you perturb it from equilibrium, as long as you don't perturb it by too much to break it out of this simple harmonic motion model. So a simple pendulum will obey simple harmonic motion to a close approximation as long as you keep the angles relatively small, with a period given by this equation dependent only on the length of the pendulum and the acceleration due to gravity, and not on the mass or the amplitude. So that's the vertical mass on a spring and the simple pendulum.